discussed several phenomena. Phenomenon number one, skin effect. That happens only we have step function excitation, and only it happens at the first moment when currents must be on the surface. Now in this case, as I shown you, on the surface. Now these currents don't have support, transmitter does not work, and we start to consider diffusion due to step function. Correct? That was second phenomenon. So two phenomena for time domain when we have step function excitation. Now there is another domain, frequency domain. So in frequency domain we briefly discussed, we have real sinusoidal oscillation has this form, but approximately for only understanding phenomenon I replaced it by periodical also function of this type. So they are similar, correct? Each impulse is sum of two-step functions. So we have almost sinusoid, a system of step functions which arise at equal intervals with some delay equal half of period. Now, we know diffusion at each point. We can treat effect caused by sinusoidal function as sum or more, sum, difference, sum it means plus, minus, all effect caused by each step function. But this behavior is due to only one step function. This behavior due to, which we are going to consider, due to many of them. Now we discussed this approach allows us to understand what happens in sinusoidal oscillations. If, for instance, this interval is very short, period is very small, effect due to one step function is surface currents. Currents don't have time to diffuse. Next step function arises, and currents remains on the surface. Besides of it, of course, that's the principle of superposition. Effect due to one step function does not depend on effect of step functions which arrive later. Currents diffuse due to each step function. But it turns out, that's the reason I gave you expression, the deeper we consider point of location, the stronger compensating effect due to them. So we have another phenomenon, compensating effect, which manifests itself in sinusoidal oscillation. That's the reason why when we deal with sinusoidal functions, if frequency is high, currents located as an early stage on the surface. When current changes slowly, it gives time to step function to diffuse before appearing opposite direction step function. They appear at greater depth. Now, trying to do what impossible, now I will show you a result of solution for sinusoidal oscillation. So suppose instead of step function we have sinusoid. These results can be obtained by two ways. One, direct and simple. Let us assume that here is sinusoidal oscillation. Let us solve Maxwell equation and get result. The same result can be obtained if we perform summation of all these step effects due to different step functions. So, one or another way, result is. So now, let us assume that we deal with sinusoidal oscillation. Peter, you can help me to increase my courage and start to speak about solution of boundary value problem. That's what I'm trying to delay. But you have to force me if you will. condition. Yes. Now, so if instead of step function we have sinusoidal oscillation, then current has completely different form. Suppose frequency oscillation omega, circle frequency omega. Then it turns out, Z T is equal current on the surface E minus P sinus omega T minus P. So current, again the same component, at each point depends on depth, time, equal current, constant current on the surface, and then this expression. So what is the P? P equal Z over delta. Delta is called skin depth. Skin depth. And skin depth is equal to gamma mu omega. To conductivity, magnetic permeability, frequency. That's the simplest, it's impossible to find simply expression. No way. So the simplest boundary value problem, which is used very often. Now, and I will explain when this expression is correct in real conditions. In effect, Ankin mentioned about it. Now, so this quantity has good name, skin depth, not skin effect, skin depth. Now it's equal to over gamma mu omega. Let us discuss this quantity, awfully useful, awfully useful. There are two parameters, in time domain, in frequency domain. This parameter, skin depth, is very important in frequency domain. There is similar parameter in time domain. Now, delta, skin depth, 2 gamma mu omega. What we see from this expression? The higher conductivity, the smaller skin depth. The higher frequency, the smaller skin depth. Now, this expression is not convenient in practical system of units if we don't do something. Something is, here mu. Mu usually frees mu naught. Mu equal mu naught equal 4 pi 10 minus 7 Henry per meter. What is the frequency? 2 pi f, or 2 pi divided by period. Now, if we replaced mu equal 4 pi 10 minus 7, if we replace omega 2 pi f, if we don't forget it's a practical system of units, therefore meters. We are working with meters. Then skin depth will be equal. You easily can check me. You see, I still remember. So you should know it. Even I remember. That's very simple for you young people remember. So if you put here 4 pi, 2 pi can take out. 10 minus 7, 10, 7 goes up. So finally we will get 10.3 divided by 2 pi square root 10 rho over f meters. That's skin depth. Why 10? Because it was 10 minus 7. 10.3 we took out. 1/10 is left. 10 rho. So skin depth increases with resistivity and decreases with frequency. That's all what we need to know about skin depth. Now, sometimes you will see why do we need it. Sometimes, in some methods, such as magnetotelluric sounding, for good reasons, instead of meters, we use kilometers. It's very attractive because he already 10.3. So another expression, is equal, unit divide 2 pi, 10 rho f kilometers. Now, if you take, it should not be this difference between two speakers. Square root of 10, around 3. So here around 6. So 1/2, a donkey road 500. So we agree with you. So that's exact expression. You go ahead also another expressions. Skin depth. However, in this simplest case, amazingly simplest case, field current, and therefore electrical field, and therefore magnetic field, don't depend on skin depth itself. They depend on ratio. Distance, z, to skin depth. Skin depth itself is not important. Important in order to understand behavior of the field, you have to ask yourself not what the skin depth, but what is the ratio between distance from the source and skin depth. This number, ratio, does not have dimension, and it has name induction number. So, naturally, always there are three scenarios. You remember when I considered with you frequency responses due to conductor, I told low frequency part spectrum, intermediate, high frequency part of spectrum. Everything was defined by not frequency, omega tau. Now in time domain, I told you early stage, intermediate, late was defined not time, time over time constant. Exactly in conducting medium, we also, everything is defined by ratio. When we consider z over delta less than unit, we speak about small parameter. When z greater than unit, large parameter, and intermediate. Now, let us use this expression. We will not use too much. But some teachers of the field in the simplest case, it's reasonable to discuss. First of all, what happens with current with depth? Let us fix frequency, conductivity, and go down. First of all, where is the depth? Here, correct? How we call this quantity? Now, not induction number, from point of sinusoidal oscillation. Phase. So phase changes from point to point. It could be 0, it could be any value, pi over 2, pi over 4, pi over 1000, etc., etc., etc. So phase, initial phase changes. That's not all. Let us look here. That's the problem where it arises. We have not exponent plus, but minus. So with increasing of distance, current and field, everything decreases. And very well, when distance induction number equal skin depth, field decreases almost 3 times, 2.7 times, exponent in power minus 1. Take power 2, 10 times. So we observe decaying effect. Why it happens? I hope I gave you at least direction. Compensating effect of impulses. The greater distance, the greater fields caused by different step functions cancel each other. Now, That's the reason why it's called skin depth, because it characterizes how quickly field decreases. Let us look at this expression from different angle. How we can present this expression? Also, can we present in different way? Sinus and cosine. So we can present it as E naught constant, E minus P, cosine P, sinus omega t, minus or plus I naught E minus P, sinus P, cosine omega t. So at each point, again, as before, there are two currents. In phase component of current and quadrature component of current, they decay in the same manner, E minus pt. However, there is a difference here. Dependence on distance also here. When parameter p is small, this term is equal almost I naught. This term is very small. So that's what, again, when Dan shown you VLF, he showed you different distribution of quadrature in phase component of the current and different depth. Therefore, they have different depth investigation. Now, this expression is used very often for understanding skin effect. It's not skin effect, it's a behavior of the field in frequency domain in one-dimensional case. Now, one small comment. This expression for current, for field, very often is used to explain depth investigation and frequency methods. And here problem could arise easily. For instance, let us take case when parameter is very small. So Z over skin depth is very small. So I choose in such a low frequency that Z over delta for some depth, and I will consider example, much less than unit. Therefore, we can bravely say, oh, our field practically does not decay up to this depth. Does it mean depth investigation is the same as skin depth? No. This quantity, skin depth, is only characterizes depth of penetration of the field, but not depth investigation. Today, afternoon or tomorrow, I will consider this question in detail. So skin depth is not designed to show you depth of investigation of one or another method. It shows you depth where field still reasonably strong. But it usually does not have any relation to depth of investigation. Skin depth could be 1,000 kilometers, but depth investigation could be few meters at the same time. Now, after these simple examples, let me give you another examples of distribution of currents in frequency and time domain. But I think something I missed in order to illustrate skin depth. And I know what I missed. Skin depth also is very important parameter which characterizes conditions where we can use, for instance, magnetotelluric soundings method. Let me show you. It will be useful also. Please imagine horizontal layer medium or a non-horizontal layer medium. That's not important. Somewhere in ionosphere you have current, alternating current. Before Second War, very famous French mathematician and geophysicist, Dr. Cagnard, who made outstanding Cagnard, who made outstanding contribution in theory of elasticity. He solved the most difficult problems of elasticity. He at the same time made very interesting suggestion. Very interesting suggestion. He told, let us measure ratio between horizontal components of electromagnetic field. I can mention about it, but let us speak a little more detail because it will give you idea about another angle skin depth. So suppose at each point of some point of observation, we measure electrical field and magnetic field. So we don't need transmitter. We don't need transmitter. Transmitter is here. And let us measure impedance by definition EX over BY. Let us measure this ratio at different frequencies. At different frequencies, not one, at different frequencies. As function of omega. So far, nothing was new. Nothing was new. But then, now I will show what new was in his suggestion. Several elements. Element number 1. You let us measure not beneath source. No, far away. That's vital requirement. Please try to remember, or some, at least it's useful. So he told, let us assume if we measure at the distances r, horizontal distance r, much greater than skin depth at each layer. Not first layer, not second, and all layers. So let us assume that condition takes place. More precisely, let us assume the distance much greater than 2 pi delta I. And this quantity is called wavelength. Even no waves in quasi-stationary approximation. But that's how it's called, 2 pi delta. So if you recall, 2 pi delta is equal 10 rho over f kilometers. You remember we had here 2 pi disappeared, I had 10.3, I wrote kilometers. Then he, because he was extremely knowledgeable person, and he made outstanding contribution in geophysics, he rigidly required measurements must be at such distances. Why? So what I'm doing now, I illustrate you practical application concept of skin depth. Now, if it takes place, but this condition is met, then something very, very interesting happens with electromagnetic field. What is interesting? You have alternating current, energy, electromagnetic field starts to propagate. Electrical field changes with time, magnetic field changes with time, energy is traveling. Doesn't matter what is the orientation of current, horizontal, vertical, no. Everything is the same. Then energy goes in all directions. Here, here. But what is interesting? When you are, there are all components of the field, vertical, horizontal, everything is present. But as soon as you are in such large distance, something happens beautiful. What is the beautiful? Energy still travels away from transmitter, but main part of it goes down. And mainly we have horizontal component electrical field and magnetic horizontal component of the field. And it goes down. So we have so-called plane wave. Exactly the same plane wave which I shown you using this stupid sheet of current which does not exist. But there is complete analogy. That's the reason what I almost was ready to miss. So analogy with what I did before, if what happens, it's so-called far zone or wave zone. Since as soon as we are far away, wave travels in this way, in downward, down. Then, regardless where you are measured, here, 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 this ratio remains the same. Even field ratio remains the same. As it happens if you had huge current plate, which I did consider together with you. That's extremely attractive. Why? Because at each point you have the same field. You are not worried where you measure. From point of distance from transmitter, effect is the same. It's not true if you measure close to transmitter. Then at each different point, this ratio will depend on distance. But if you are far away, a horizontal component, electrical and magnetic field, decay in the same manner with distance. That's vital feature of the far zone, or more precisely, wave zone. So For example, electrical horizontal component could decay unit divide R4. R, distance to ionosphere current. And horizontal component. So, taking ratio, you get rid of influence. That's the reason why Cagniard took ratio. Because nobody knows where is this lovely, powerful source. Taking ratio, you get rid of its influence. Also, taking ratio, you get rid of unknown current of transmitter. Magnitude of the current on transmitter. It could be 10,000 amperes, it could be millions. You took ratio, it does not depend. And what it turns out, that's only one method when we have extremely favorable conditions, when skin depth really defines depth of investigation. So what I'm going to say contradicts what I told before. I told in our mining exploration, in most other methods, skin depth only defines depth of investigation, but depth of penetration, but depth investigation could be much, much smaller. In this case of plane wave in horizontal layer medium, they coincide. Now, and what it turns out, this ratio is a function of all layers, resistivity of all layers. When we measure at low frequency, high frequency, as you remember, skin depth is small, and we get information about rho 1. When skin depth is very large, something happens. That's again was genius intuition of Cagniard. Nobody knew it before. You measure on the surface. Common sense tells low frequency, high frequency. What is the matter? Always it will be influence of several layers. First layer, you are sitting on the layer. You measure electrical magnetic field on the top of the first layer. Why its influence must disappear? But it turns out, when frequency goes down, all layers except last become transparent. So, when frequency Z, when omega goes to infinity, impedance gives you rho 1. When frequency goes to 0, impedance gives you resistivity of the last layer. So this simple idea based on pure concept skin depth was extremely popular after Second War. Many oil companies used. There were many other companies which all their activity was based on this concept. Then somebody tried to invent method which it looks like similar to magnetotelluric sound. This method is called control source MT. So let us do the same. But let us again remember what was the reason for taking ratio? To get rid of unknown current. But when we have already transmitter which we use, we don't need to take ratio. We know current. So one reason for there is no any justification for this step. But more important, another moment. Plane wave behavior, dependence on skin depth, is valid only when distance is much greater than wavelength or skin depth. Practically, it's impossible, on one hand, to create sufficient depth investigation and at the same time to work in wave zone from source which is located at a distance few kilometers. Simple calculations show it. So What happens if this condition is not correct? Very simple. Even you have horizontal layer medium, you have different values of the field at different distances. And that already makes whole picture more complicated. So that's small illustration of skin depth. Now we have time. No, we will make break. Because during this hour, two completely different subjects. Completely different subjects. One will be, both of them I will cover, not very deeply. First of all, we discuss skin effect and diffusion. Let us assume that we know how to solve the forward problem if we know how to calculate distribution of currents inside of conductor. Let me show what happens in the simple case. Suppose we have sphere with radius A, conductivity gamma. Suppose we have a loop, transmitter loop. Then let us assume we turn off current in transmitter as step function. Then let us ask ourselves, what would be geometry of currents induced in our body? This is the our body. That's free space. Clear? We didn't come to more general model yet. So first of all, if you remember, somebody already suggested me, I completely agree, primary electrical field due to loop has one component. Not magnetic, electrical. Therefore, when this electrical field acts on conductor, electrons starts to move in the same direction. So induced currents which arise in our body also circles. Clear? Now, it's not. Now, what happens at the first moment? Let me ask you a question. That's axis. So, there are currents everywhere. Again, we are talking about the skin effect. The skin effect. Where currents at the first moment will have greater density? At the center or here? First of all, it is not the same. It's the same when I consider simple idealistical plane wave approximation with sheet. Now, loop, suppose loop far away or large loop, uniform field, where density will be stronger, here or here, how it will change shortly along this path. Huh? Yes. It will be extremely small here. Why? Because flux through this ring is very small area. So current density will increase from 0 as sinus theta. Please recall expression for an electrical field which I gave you. We will use it today, tomorrow, I don't remember. Mu m point 4 pi r square sinus theta. That's primary electrical field. It's 0 beneath dipole, for instance. That's for dipole, not for loop, but similar, if far away. So let us take that's so at the first moment, induced currents arise on the surface. They are in this simple case distributed in their circles. They are distributed such way that maximum here and minimum here. Now let us ask ourselves, what happens later? What happens later? Let us choose any radius A, and find out how current will distribute it along this radius. Is it clear? That's what I'm going to show you as illustration. So, let me plot graph. Here, R over A radius, R any point. So R changes from 0 to I. That's 1, that's point 1, point 2, point 3, and etc. Point 9. So let us take case when time is much less than time constant. So case number 1, here 1, here current phi R over current on the surface. So we are interested how current at each moment inside differs from current on the surface. That's our interest. Case number 1, T over tau much less than unit. What do you think? What would be the behavior? First of all, please predict, and then I will draw. Not very accurately, but draw. What do you think? Could you help me? So, ratio between current. So, this skin effect is gone. Now we take time a little later after turn off. So there is diffusion. There is diffusion, correct? So where are these our lovely induced currents when time is not 0 but very, very small? Still near surface. So you can expect that graph will be that's when time over tau very small. Then time increases. Then what happens with our lovely currents? They start to show up where? Deeper. Tau 2 over tau. If we take next time, even we will see some maximum and again 1. And if we take very large time, we will have this graph. Now, this, if you compare, for example, 1, if you compare these two graphs, don't compare magnitude of current. Magnitude of current with time goes down because energy transforms into heat. This graph only shows you relationship between currents at some point and current on the surface. Moreover, as I told you, should believe me, at least try to. At late stage, magnetic field decays how? As exponent, as one exponent. Magnetic field caused by these currents. So it turns out at the late stage, when time exceeds tau, all currents in conductor decay in the same exponential way. Otherwise, magnetic field caused by them will not decay as exponent because Beel's are low. So at the late stage, when time exceeds tau or close one, all currents, regardless where you took them, near center, near surface, decay in the same manner as exponent. So at each point, current proportional E minus T over tau. It takes place near, here, here, here. So all of them decay in the same manner. It means, what it means? Again, important conclusion, that if you change time, relative contribution caused by different parts of conductor does not change. Because if each of the, take two current rings and measure at this point, if both of them change in the same manner, for example, after 1 second, they both currents increase 2 times. Therefore, in magnetic field caused by them decrease 2 times, but ratio remains the same. So you cannot enchance influence of one part of the body with respect to another if you are already at late stage. Is it understandable or it's not clear? Now, that's example of time domain. But we have frequency domain. Let us look what happens for the same conductor in frequency domain and time domain. By the way, what I told a few seconds ago is valid for plate, for dike, for pocket, any pocket. Always it's true. As soon as you are in late stage, induced currents which arise, which creates magnetic field, all of them decay in the same manner as one exponent. Completely different story at early intermediate stage. But at late stage, good or bad, that's the fact. All currents in all places decays the same manner. So a relative contribution caused by them from different parts of the body for magnetic field remains the same. Now let me show you what happens with in-phase component. The same loop, the same target, everything the same. Now again, R over A. Of course, no more tau. We drive sinusoidal current. So let us take low frequency part of spectrum. Skin depth, large. So we will have in phase component of currents at point R over in phase component current on the surface, exactly the same. Only I consider component of current which synchronically changes with current in transmitter. No surprise. We will have the same behavior as here. So, let us say A over skin depth around 0.5. So, skin depth inside of sphere, A radius, and currents distributed in the same way as in time domain and late stage. Now, when I increase frequency, what should happen? Currents must tend to surface. That's what we observe. So here we increase ratio because frequency goes up. Now I touched one subject. I understand it's a very high flux of information, perhaps, but, sorry, something? A delta equal 0.5 as example. Skin depth, I'm sorry, I write badly. No way to change after 60. No way to change, even bad stuff. So, I touching very important subject. In phase component of the field behaves very similar time domain. If you remember, yesterday I tried to emphasize measuring quadrature component. You have one ratio between usable signal and noise. In phase component, different. And measuring in phase component, you can reduce better sometimes noise than quadrature, and even better in time domain. So in phase component, measuring in phase component is natural step approaching to time domain. I think, at least when I start to discuss with you, frequency also mining, no difference, I would say. If we were able to measure in phase component with such accuracy, then in transient responses, we would create the equivalent methods. But nobody yet succeeded to do it. So this picture is one of indication of this fact. So we will return to this subject, I hope, to today. Now I have to do something what I do regularly in my classes in School of Mines. Now and then, then let me stop for a moment. All time I trying to explain you behavior of a electromagnetic fields. But I delay one subject, which I do believe it's important. How we get these numbers? How do we get these numbers? And I would like to make one statement, at least in my understanding. In order to get this number, you have to have manual. The same manual which you have to have in order to perform measurements in the field. No difference. In effect, everybody who were involved in developing theory of geophysical methods followed some manual, at least in main part. There are some good improvements, but there are many ways the same good improvement in manual using new equipment. So behind of my speech is statement. Each engineer at least must know how, in general, how to get. What is the manual, instruction, which we have to follow in order to get these numbers, these graphs, this. So let me outline main features of solving the forward problem. I will remind you something what you knew or don't know, doesn't matter. It doesn't matter. It's a manual. That's it. Manual instruction. As soon as I learn in your age, somewhere in your age, this rule, I never change it. I never pretend that I solved some problems. At least I understood how to solve. I used them. No, I didn't ever solve new problem, but I used all problems very easily when I learned how to do it. So let me share with you. But before, one fact. A couple centuries ago, a subject which does not have a direct relation to what we are going to do. A couple centuries ago, Euler discovered amazing formula. Amazing formula. Which one or another way you met in university. The formula is EIX I is equal square root of minus 1, imaginary unit. There is such number. I see pale faces, especially young girls, so we are in trouble. But don't worry, it's a complex variable, it's a standard, it's a basis, is equal cosine x plus I sinus x, when x is a real number. Amazing formula. For a long time, people didn't believe, we didn't understand how cosine x plus strange number, imaginary unit, I sinus x equal this almost crazy number, exponent in power ix. It's amazing fundamental relation which was discovered by Euler. It's if you pretend you are engineers, you must know. Now, because it's a basis. Now, if I write I omega t using this formula, I will write cosine omega t plus I sinus omega t. Because x omega t, omega frequency t time, Euler formula. Now, suppose I have another expression. I use this Euler form. I omega t plus phi. Understandable what I'm writing? Therefore, I can write it's equal cosine omega t plus phi plus I sinus omega t plus phi. Understandable? So far, so good. Now, let me multiply by some constant, a real number. Real number. I will write I omega t plus phi equal a cosine omega t plus phi plus I sinus omega t plus phi. As soon as you believe Euler, you have to believe this expression. What is it? Amplitude of oscillation. What is it? Phase. Correct? Now let me do the following. Let me rewrite this expression. Do you agree with me? If E equal Ix plus y, I can write Eix times Ey. That's the same or not? Now, let me do the same here. Can I rewrite this expression? Left expression is A Ei phi times I omega t. You follow me what I'm doing? A I omega t I phi. True? If you are lost, stop me, please. Now it's equal A cosine omega t plus phi. Just a second. That's small preparation, and then we will start formulation forward problem. Plus A I sinus omega t plus phi. Let us call this complex number, it's complex number, agree? Because according earlier formula, E I phi equal AA cosine phi plus I sinus phi. Let us call this quantity complex amplitude of spectrum, complex amplitude of the field. Why complex? Because it's a complex. Why it's complex amplitude of the field? Because it contains amazing information about amplitude and phase. So it's called A star. So A star times I omega t equal A cosine omega t plus phi plus I A sinus omega t plus phi. All engineers do, electronic engineer, physicists, everybody knows this number. It's very important. What is about this number? There is another very important relation. It follows from here. What is the magnitude of this number? 1. Why? Take square of cosine squared sinus, take square root. Very famous relation. So, this quantity is complex amplitude. Now I would like to ask you, suppose in my current current changes I equal I naught cosine omega t plus phi. Watch here. Can I present this expression? Very simple, very natural. Can I present in a very strange form? It's equal real part of A star times I omega t. What is written here? Complex number which consists from real part and imaginary part. True? What I say here, RE, take real part of right expression, this expression. So, let us do it. Let us compare these two expressions. Here, current, amplitude, here, function of time, and phase is hidden inside of argument. What I did, I presented the same expression in completely different form. It's a product of two functions. One of them is independent on, no, that function depends on frequency, but, time. And then dependence on time in amazingly simple manner, exponent. That's all what I need in order to describe main feature of solving forward problem. Did I explain clearly? Now, what do you think? What do you think? You would like, please imagine, you have current loop, and is located near our body. What is your intuition? Your intuition tells you it's easy to find field when you use frequency oscillation in current loop or impulse or step function. What do you think? First of all, don't let us discuss this question. So you have current loop. You drive sinusoidal current, which was started millions of years ago, it will continue. And, or another scenario, and you will induce currents, etc., 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 or you have step function. What is your feeling? Iron rule. It's easy to find field in frequency domain. Why? Because it's periodical function. You know, I told you, you remember I told you, if you have linear system, or all our systems are linear, if your input sinusoid, output will be sinusoid. If you have step function, sorry, you saw graphs, diffusion, unknown behavior. So it's natural, and all problems, 99.9 problems of electromagnetics, mining, structural, logging, are solved in frequency domain. Now, trick is, from physical point of view, it's more difficult to imagine diffusion in frequency domain. I tried to explain you compensation, etc., etc., etc. But as concerns mathematics, it turns out it's easy to do it in frequency domain. Because, I told you, you already know what would happen. It's already great achievement. Now, but who cares about frequency solution if you're using time domain equipment? What we have to do next? There is, again, great Fourier, who told, if you would like to find for any arbitrary input, please use Fourier transform. So solution of forward problems in geophysics, by the way, in seismic, the same in general case, not geometrical optics. Step number one, solve problem in frequency domain, and then use Fourier transform, 2 stages. Now, except some special cases, sphere, cylinder, horizontal layer, medium, everything has to be done using rather complicated algorithm. In the case of horizontal layer medium, in the case of sphere, cylinder, you can solve using very famous method separation of variables. However, in both cases, solution is not for calculator. You have to use computer. So engineer, first of all, has to formulate boundary value problem, solve it one or another way, and then using computer calculating frequency spectrum, dependence of the field and different frequencies, and then use Fourier integral. That's the main steps. Let me discuss with you step number one, how we formulate boundary value problem. First of all, let us take, we have 4 minutes, then we have lunch. We have 1 o'clock lunch. I don't remember when we have. 1:15. So we will stop 1:15. 25 minutes is okay? Let us try. It's okay that we have more than 1 hour. Maybe they are already dead. So So I more or less I know subjects, so what I will tell myself. You listen? You will listen, eh? Yes. Yes, thank you. So 25 minutes, yes? So I hope we will succeed. So let us formulate the boundary value problem. Suppose we have a loop, current loop, with current which changes as sinusoidal oscillation, which I assume, so cosine omega t. I cosine omega t, I naught, that's my current. Now, there is conducting medium, conductivity gamma 1, here conductor gamma 2. I know position of the surface interface. If I say I would like to solve the forward problem, I know all parameters. That's vital condition. I know where is my source generator, what is the shape of the source, dimension, I know current, I know conductivity, I know position of each point of my boundary. Agree? Agree. Now, now tell me please, if I placed here transmitter, how many fields create transmitter at this point for given geoelectrical section? So it creates magnetic, electrical field, induced current arise. So I will measure here electrical, magnetic field. How many fields this transmitter creates for given model? One. At each point you have one field. You have one gravitational field, you have one magnetic field, one electrical field, one electromagnetic field. Change current twice. Sorry, you will have twice bigger field. But for given current, for given model, you have one field. So don't worry about very complicated word uniqueness, non-uniqueness. Engineer must tell self, if I placed in one place, I will get at each point one field, not two, not three, not four. Let us remember it. We don't know field, but we know its behavior. Let us remember, we know its behavior. We don't know value. But what do we know at this point about electrical and magnetic field? Huh? Sine, that's we know. But do we know something more? You are completely right. For harmonical oscillation, we do know its sinusoidal function. But do you know that this field must obey Faraday's law, Coulomb's law, Biot-Savart law? I forgot what else. So, correct? So, it must obey physical law. Did we find some mathematical form which contains all these physical laws? Maxwell equations, or in other words, for quasi-stationary field, these all equations were replaced by one equation. What is the equation? Huh? Sorry? D'Alembert covers everything, diffusion, propagation, but if we neglect by displacement currents, we will be modest. Diffusion equation, because all four Maxwell equations gives us one equation. Do you follow me? So we don't know value of the field. We don't know value of the field. But we do know if it's our field, it must obey Faraday's law, Ohm's law, Biot-Savart law, correct? And all this information is contained in diffusion equation. Clear? So let us write this diffusion equation. So, for instance, for electrical field, it's equal pardon, it's not correct. Always I write, I'm a positive person, I like to write always plus. It's equal gamma mu dI dt. So you see, we know already a lot. At all points of the medium except what? Interfaces, because you remember I told you Maxwell equations have completely different form at interfaces, continuity, tangential component, electrical. So, first requirement, everywhere inside of the layer, for example, in this medium, outside conductor, at all points outside conductor, but not where transmitter is located. No, it's something special. At all points transmitter, we have this equation. When you write this equation, you simply tell yourself, my field must obey Faraday's law, Biot-Savart law, Coulomb's law, etc., etc., etc. Clear? If your field which you find does not satisfy this equation, you don't respect great masters. That's simple. Maybe you will find another field of the wind, who knows. So it's a lot, many points. Now what about inside? So here I have to write gamma 1, clear? Because outside of conductor, conductivity gamma 1. What about inside? Of conductor? Electrical field, sorry, must satisfy heat equation. It must be equal gamma 2 mu d dt. We are lucky, the same equation, only coefficient is different. So we don't know yet field, but we know this field must obey this equation. That's the essence of the forward problem. Now, it's time for me to stop. Now, so let me write it's 1. It's A, that's B. Now, so let me use another words. These two equations describe behavior of the field in regular points in each medium. Clear? Now, condition number 2. I didn't describe field in 3 places yet. There is very important place, interface. Again, we don't know field, but we, knowing physical laws, do know something. What we do know about tangential component electrical field at interface? Equal. As soon as they are not equal, if you find something, you argue with physical law. So, you have to write on S, tangential component field on one side must be equal another side. This simple equality is in essence heat equation only for surface. It's a surface analogy. This equation does not work. Why? Because one of components could be discontinuous and derivatives don't exist. So you replace it. It's not something else. What we know about magnetic field? we have to write the same equation, of course. You understand, gamma 1 mu dB dt, both equations satisfies gamma 1, here gamma 2 mu dB dt. Now, what is the surface analogy of this equation interface? Tangential component of magnetic field for all normal cases are continuous, equal. It's not very much boring. It works? Good. Now, so we did a lot. We know, we don't know yet field, but we know it must satisfy, both electrical magnetic field must satisfy condition, heat equation where? Inside. But at interfaces must be continuous. As soon as it's wrong, you found fields, tangential component of which are not equal in each other, you are in trouble. Biot-Savart law wrong, and Faraday's law wrong. As I do what I share with you, how I understand. To me, each equality is a physical law. If it's not, if I don't know boundary condition interface, I have to tell myself, sorry, I don't understand physical law. Very simple. It's not some formulas from pure mathematics. No, it came from physical laws. It's a mathematical formula, physical law. So we know a lot. Our field must satisfy inside of a heat equation at the boundary these conditions. Now, let me ask you questions. Let me ask you a question. Just a second. Don't think about transmitter. How many electromagnetic quasi-stationary, it means fields which don't take into account propagation, how many fields satisfy these two conditions? I call it two conditions. One and two. Huh? Slowly. Don't rush. It's a difficult question, but very, very important. Very, very important. So please imagine model. What? That's our body. Our body. That's conducting medium. You know conductivity of this body, its shape. You know conductivity of surrounding medium. My question is, how many electromagnetic fields, only please imagine, instead of air, you have conducting medium. With given conductivity, 1 ohmmeter, here 10 minus 4 ohmmeters, suppose. So, how many fields satisfy these two equations? Okay. Okay. Now, tell me please, again, you feel model, conducting medium. Inside of conducting medium, you have fixed conductor. Please imagine I put transmitter here. Transmitter here. Does it create a round electromagnetic field? Does this magnetic field satisfy heat equation? It must. Does it satisfy condition at the boundary? It must. Now I move transmitter a little a different place. What happens with fields at this point? It must satisfy must satisfy inside, must be boundary condition. So you can change position transmitter a little, or how you wish somewhere. All fields, all quasi-stationary fields must satisfy this condition. Don't move transmitter, change form of behavior of the current transmitter, not sinusoid exponent. It must satisfy. So infinite number of fields, that's the power of Maxwell equations. How many fields satisfy Maxwell equations? All, it's a lot. That's the universal power of Maxwell equation. The same true for heat equation. So these two conditions have infinite number solutions. How as physicists, or I geophysicists more proper, say, how I see it? I see very simple. I change position of transmitter. I got new field. And this field must satisfy heat equation, must satisfy condition at the boundary. Otherwise it will not obey physical laws. So far we formulated two conditions which have infinite number solution. It's better now or down? Now let us make almost crucial, very important, fundamental improvement. Let us say something about our transmitter. Where is this transmitter located, and what is the power of this transmitter? Now I fixed position of transmitter. Suppose it's a dipole, small loop. Moment, current, area. Let me call R, distance for any point. This point, that point, doesn't matter. Now, tell me please, if I start to approach point P close to transmitter, I choose system of coordinates, that's my origin. If what at each point field consists of how many parts? Now you have to think again as geophysicists. No, let us take electrical field, for instance. It caused by what and what? Again, geophysical language. Field caused by what and what? It caused by current in transmitter plus all currents which arise in conducting medium. Can we say that our electrical field or magnetic field at each point consists of two parts? Primary field caused by transmitter, which we counsel in M31, M34, many other things, systems, plus secondary field caused by currents in each conductor. Now I start to approach point P close to transmitter. What would happen? Very good. Primary field will be dominant. So now I choose origin. Watch carefully. I will try to speak carefully. I choose origin where my generator is located. So it means I do know where is my generator. I know moment of generator. I know, it means I know current, area, and orientation. So when IR goes to 0, my field must tend to what? Primary field. Now, what is the meaning of this condition? I tell where is my generator, correct? Because I choose an origin where transmitter is located. Moreover, I tell what is the power of transmitter. How I know current area? Because primary field depends on moment of the field. Now, very important question. For all practical purposes, these three conditions define how many fields. Now you placed in your given medium transmitter at this point, and you told what is the moment, how it changes with time, you know current, how many, again my old first question, how many fields you will measure at this point? Oh, one, not two, not three. That's time came to say one. So what you now almost know. I will make one small correction, but it's not important for us, not for mathematical formulation. These three conditions define what uniquely our field. If you find, not exactly, I will make now after a few minutes, small correction. If you find electrical field, who knows, which satisfy at everywhere heat equations, if it satisfies these conditions at the boundary, and its field is such that approaching to the source it coincides with your primary field, then you can say, I found my field. Understandable? Now, only one additional moment. These two equations, lovely heat equations, tell about behavior of the field at all reasonable distances, normal distances from the source. But who knows, maybe extremely far away, there are other generators. So, since we don't have them, we have to say, again, common sense tells. If you are going far away, field must go to 0, correct? Must disappear. But this, when R goes to infinity, field must, electrical, magnetic field, must go to 0. Now we can bravely say we did formulate boundary value problem. You see how it's simple. At least formulate. Formulate, not find, formulate. In effect, we simply wrote story about field. We described its behavior. To formulate boundary value problem it means to describe behavior of the field. What we described, we told, at this point there is what? Generator, electrical dipole, magnetic dipole, current line, loop, doesn't matter. Field, magnetic, of course, electrical field, tells you these two values, tell you everything about field about your generator. Common sense tells, if I know where my generator, I know it creates only one field, not two, not three. Then you have to tell everywhere except interfaces, it must satisfy diffusion equation if we don't take into account propagation. Now, at interfaces, another page of story, another page or chapter of story. Field at interfaces must be continuous, otherwise Biot-Savart law and Faraday's law would not be valid. And now finally, field far away must be zero. There is no any other way. It's to find field. It's a manual. It's a manual, pure manual, as what you use voltmeter, ampermeter, M31, Seratem, or who knows, control source MT. You know what you have to push button in order equipment would work. Exactly the same. First button, please find solution of this equation. Please find field which satisfies this condition. Please don't forget, take into account your generator. Your field must be such that approaching to generator, it must coincide with dominant part, primary field. Also, don't forget, no sources far away. This condition is called condition near source. This condition at infinity, and that's boundary condition, so that's heat equation. So we will repeat a little, we'll continue a little after.